session. This room doesn't have another talk, so if you want to go downstairs to room 103 for Rebecca's third presentation, because the reception won't start until after all the presentations. Okay, so this is Jesse Gourevitch. Jesse is a second-year PhD student working with Taylor Ricketts. His research focuses on ecosystem service modeling and optimizing investments in conservation. Two truths and a lie. Jesse can shuck 41 clams in 3 minutes. Jesse has gone 3 weeks without showering. This is a common theme. Jesse has roasted 2 whole pigs. And with that, we will have Jesse's talk, Spatial Targeting of Forest Restoration Equitably Distributes Flood Mitigation Benefits.
Thanks. So I'm going to be talking about how we can make investments in conservation such that the benefits from conservation are more equitably distributed. And I'm going to be using forest restoration in Vermont as a case study and looking at how that can mitigate flooding. So I'm interested in how we can make conservation more equitable. Just some background. Prior to about 20 years ago, the conservation community was primarily interested in conserving biodiversity. Around 2000, 2005, that started to shift with having dual objectives of protecting biodiversity, but also considering ecosystem services or the benefits that nature provides to people in their decision making. But in the last 20 years, the conservation community has not done a great job of evaluating how nature and human well-being are linked. In a lot of the literature, the beneficiaries of conservation and ecosystem services are talked about very homogenously, and also human well-being is typically measured in aggregate and not breaking down different dimensions of human well-being. So what I'm arguing is that this approach risks exacerbating inequality in the communities that the conservation community is seeking to improve, and that they need to more explicitly consider equity and justice in their decision-making. So that includes disaggregating beneficiaries into different socioeconomic and demographic groups, depending on their vulnerability and preferences to changes in ecosystem services, and disaggregating the components of human well-being that are linked to nature. So here I particularly focus on distributive justice, so that means distributing the benefits of conservation equitably. As Jonathan talked about earlier, there's many other dimensions of justice as well. So as I mentioned, I'm using flood mitigation in Vermont as a case study for this project. Just some background, Vermont is losing about 1,500 acres of forest every year. That's primarily due to suburban development. As you all know, catastrophic floods are becoming more and more frequent in Vermont. In the last 50 years, there's been 3 what we call floods that are of 100-year magnitude. And a lot of research from the Gun Institute and others at Rubenstein have shown that forests have the potential to mitigate damages from flooding. So this forest loss has the potential to damage some of the ecosystem services. And land managers and other big conservation organizations are considering investing in forest restoration to provide multiple benefits, such as flood mitigation. This project is in partnership with the Nature Conservancy, who's actively considering these decisions in where to restore along riparian corridors. So this is the study area. It's the Lewes Creek Watershed. It's primarily located in Addison County, intersecting Starksboro, Moncton, and Charlotte primarily. As you can see, it's a primarily forested watershed, but particularly along the riparian corridor, that blue line, you can see that a lot of that has been converted to pasture and row crop agriculture. These red dots here represent properties that are within the baseline 100-year floodplain, and so they're at risk for future flooding events. And there's a mobile home park community that's 40 low-income properties that's particularly at risk from a 100-year flood event. So my research questions are, to what extent can forest restoration mitigate flooding in Lewes Creek? How are the benefits of flood mitigation distributed among households? And where in the watershed should restoration be targeted to provide these benefits? There's a couple challenges to making this type of decision. Unsurprisingly, restoration is pretty expensive. It requires the intervention cost of actually doing the restoration, and then also costs purchasing easements from landowners. The effects of restoration are spatially variable, so restoring in one part of the watershed may have a very different effect than restoring in another part of a watershed. And it's spatially dependent, and so what I mean by that is the effect of restoring a particular part of a watershed is dependent on the state of the rest of that watershed. And finally, the households that are to receive this benefit of flood mitigation vary in their vulnerability to flooding. So here I'm evaluating vulnerability in terms of property values and using that as a proxy for wealth. So there's a couple of factors that go into deciding where to restore. These are identifying possible interventions. So in this case, that's forest restoration. Defining the objectives, so mitigating flooding to these houses. Mapping the decision units, so where can restoration occur? The decision units in this study are riparian sections along the stream corridor. So there's 200 possible places that can be restored in this watershed. And finally, we need to specify a cost constraint. So the Nature Conservancy has specified a budget of $500,000. And so in making this decision, we need to keep under that budget. So all of these inputs then get fed into a genetic optimization algorithm, and that essentially finds the best places to restore for the lowest possible cost. This is an important part of the project, but the details of this algorithm are a little outside the scope. So there's a number of different steps that go into evaluating a particular restoration scenario and estimating that effect on households. So I'm going to walk through this kind of step by step. The first part is looking at how forest restoration impacts the flood regime. And for this, we use HECRAS, which is a hydraulic model developed by the Army Corps of Engineers. And it predicts flooding extent and depth while taking into account land cover. So here is a land cover map, just representative of a part of a river corridor. You have pasture, developed lands, forests, and wetlands. And so each of these land cover types is associated with a different friction or roughness coefficient. So this is basically referring to how much the water is slowed down as it flows over this type of land cover in a flooding event. So for example, as water flows over a pasture, it gets slowed down much more than flowing over a parking lot, for example. And as you can see, forest has the highest roughness coefficient of 0.36. So among these land cover types, it has the greatest potential to mitigate flooding. So if you look at this cross-section here, as it crosses the river, it overlaps these two different land cover types. And so we model this cross-section in 2 dimensions, where that dip at the bottom is the bottom of the river. And then on the left bank, you have the pasture. So it's represented as this N value of 0.31. On the right bank, you have an N value of 0.07, so that's the developed area. So in our restoration scenario, we replace those N coefficients with the N coefficient for forest. And so then we force this through the model and then look at the flood outputs that result from that change. So these are the outputs from HECRAS. This is a 100-year flood under the baseline scenario, so this is current land cover, and then 100-year flood under a restored scenario. So you can see that the flood depth and extent decreases considerably. Those red 3 dots are properties that were originally within the floodplain, and under this scenario, they're doing pretty well. They're no longer within the floodplain. So then we look at how the value of that reduction in damages to those households. So we use a set of what are called depth damage functions, which are essentially relate how flood depth corresponds to a % damage in property. And this is derived from flood insurance claims from the National Flood Insurance Program. So here we disaggregate among single-family homes, mobile homes, and commercial properties. And as you see, these functions plateau above about 3 meters. So we'll compare under a baseline scenario and a restored scenario how that reduction in flood depth affects % property damage. We then use tax records to evaluate the value of those reductions in damages. The piece of this that I'm really interested in is looking at how the value of those damages actually translates to utility to these households. So I'm assuming that a valuation approach is not a very good proxy for utility, meaning that for example, a $10,000 reduction in damages is much more valuable to someone who owns a $50,000 home than to someone who owns a $1 million home. So this curve here is basically showing the diminishing marginal utility of avoided damages. So for each additional dollar of avoided damages, that utility flattens out. So I use a series of what are called equity weighting functions, and basically they assume that these utility curves have different shapes depending on your wealth or income. So what really drives these types of functions is this eta coefficient, and what that does is essentially gives preferential treatment to lower income households. So with an eta value of 1, basically a 10% reduction in damages is equal to all households. With an eta value of 3, that difference is even greater. So you can think about this in terms of like a progressive tax, for example. Like the highest income people in society pay a 35% tax, the lowest income people pay a 12% tax. And so that's essentially accounting for these differences in the shape of the marginal utility curves. So I ran these functions through the optimization algorithm and tried to find the best restoration scenarios that maximize utility to the households while keeping under this budget. So this is a result where the eta value is 0. So that's essentially saying that $1 is $1 is $1 to everyone. And as you can see up here, property values on the x-axis and reduction in flood damages on the y-axis, and each of these dots represents a household within the baseline 100-year floodplain. So as you can see, most of the benefits are occurring to the top half of property values in this scenario. I then looked at what if eta is 1, so essentially maximizing the aggregate percent damages across all households. So in this scenario, you can see that the benefits are much more evenly distributed. Households in the bottom half of the value are getting more benefits, and the benefits for the top half are brought down a little bit. And then we can look at an eta value of 2. So this is giving really preferential treatment to the lowest value properties. As you can see here that their benefits are the greatest, and that the top half receives 0 benefits under this scenario. So as someone making this decision, they have to choose how much they're really weighting equity in this type of scenario. And that has implications for where you decide to restore. So the colored cross sections in these 3 maps are where you restore under those 3 scenarios to get those best outcomes, depending on where eta is. So it's a little hard to see, but if you look at this top right corner in all 3 scenarios, you can see that there's greater restoration there, and that's where the mobile home park is located. So just to sum up, I show that forest restoration does have the potential to mitigate flooding. There's, of course, other mechanisms to mitigate flooding, but forest restoration does have several co-benefits as well. I'd like to make the argument that ignoring the heterogeneity among these beneficiaries, so not accounting for the distribution of income within this community, may exacerbate inequality with this community and give preferential treatment to the wealthiest homeowners who are in fact least vulnerable to flooding. And finally, accounting for this heterogeneity among these beneficiaries and the differences in their vulnerability may have big implications for where a group like the Nature Conservancy decides where to restore. Thanks. Sam.
First of all, that's really cool. Second of all, you said restoration is expensive, and I was wondering about, does the Nature Conservancy have to buy land or these development rights to land if they're going to plant forest on it? And then the other question is, I don't know much about ecological restoration, and if there's tricks to do it better or worse or without invasive species, but I do know that in Vermont, you just stop bushwhack or brush hogging area, and it does turn into forest most of the time.
Yeah, so the first part of that question, the Nature Conservancy would be primarily purchasing easements from farmers and other landowners. So that easement would, in theory, offset their opportunity cost of taking that land out of production. Then that's coupled with like the intervention cost of actually doing the restoration. In terms of the specific type of restoration that's occurring in terms of like tree species and how many you're planting and at what intervals, that's like really a much more fine scale analysis. And in general, kind of like even like the top of the line hydrologic models are not good at capturing those types of differences. But I agree, it's an important consideration.
Fortunately, we are out of time again. But that'll be the end of this session.